Hello, hello.
Now, we shall continue. We have already seen how power can be transacted through a bond, and Professor Henry Painter, he insisted that the power arrow or the power bond should be different from a conventional bond. A conventional signal bond carries information of just one variable, whereas a power bond carries information of two variables, and the product of these two variables is always power. With this, we will now come to the next aspect, that is the alphabet of bond graph, and these are the elements of bond graph. We have two sources, a source of effort and a source of flow. We will discuss what these are. We have elements which are an inertia element, a stiffness element or a compliance element C, and a dissipation element R. And we also have junctions given by 1 junction and 0 junction. We have two other elements, one which is a transformer represented by a TF, and a gyrator which is represented by GY. And you see that these are the only 9 elements in addition to the power bond in the bond graph set, complete set. So here you have the two sources, a source of effort and flow, you have an inertia, compliance and dissipation, you have a 1 junction, a 0 junction, a transformer and a gyrator, and we will be explaining to you each of these details about each of these elements subsequently. There is the other issue of causality, cause and effect, and let me introduce what this effect, what this aspect of causality is. You see, whenever there is a transaction of power between two subsystems, let us say you have a subsystem A and a subsystem B, and there is an exchange of power between them, and we know that we can represent this exchange of power with the help of this power bond. We have an effort variable and a flow variable. But the characteristic of this transaction in case of physical systems is that the direction of flow of effort variable and the direction of the flow variable, that means whether A is providing the information of effort to B or whether B is providing the information of effort to A or whether both are being provided, who is providing this information to whom, okay. This comes under the issue of causality, cause and effect. And suppose you have effort, the information of effort being transmitted from the system A to the system B, okay. And you see here that we have represented this using a signal, we have shown using a signal bond, and this signal bond is representing just information of one variable, which is the effort variable, and the signal bond is a full arrow, okay. So the information of effort is going from subsystem A to the subsystem B. In physical systems, it is necessary, it is compulsory that if the information of one of the variables of power goes from one end to the other information, the information of the other variable has to go in the other direction. So in this case, it is absolutely necessary for physical systems. That means in this particular case, the subsystem B should provide the information of flow to subsystem A. This is a necessary requirement for the transaction of power between two physical subsystems. And it may seem very strange or very surprising to you, whether you may be actually wondering whether how valid is this. But let us just give it some simple argument. Suppose if subsystem A, let's take an example, let's say that subsystem A is interacting physically with subsystem B. There is a transaction of energy, there is a transaction of power. And let's assume that both effort and flow variables are being determined by effort A itself. Let's say that effort A is saying that I am going to impose this much effort and I am also going to impose this much flow. Is that possible for physical systems? Can it interact with another subsystem in this case? The answer is it cannot. Because if that was possible, you would have been able to do wonders. Why? Let's take an example. You could have applied several volts, okay, or very small value of potential difference to the other end, to the end B, and also you could have imposed that only so much current should pass through it. So that means you would have had a total control of power in your hands. That means I am going to also decide how much is the potential difference on B and also going to decide how much is the current drawn. But we know that this never happens, because if that were to happen, you could have achieved, you could have with very little power, you could have applied very high voltage, very high currents, okay. That is not possible. In the mechanical domain, with the help of very small force, you could have said that I am going to apply only a few newtons of force, but I am going to have fantastic speed and I am going to accelerate, I am going to move a huge mass. So you see, the power that is actually being imposed is very less, and then you find that it never works like that, because whenever two physical subsystems are interacting with each other, it is necessary that one of the subsystems should provide information of one variable, one of them should determine one variable information, and the other subsystem should complement it. That means it should provide the complement of power. Okay. So here in this case, if effort is determined by A, flow has to be determined by B. Okay. Only then it will be possible for us to have a physical system. Only then it will be able to obey the laws of physics. Okay. So this is an absolute essential requirement, and I am not very sure how many of you are aware of this. And so for interaction between two physical systems in any energy domain, in any domain of energy, you require a clear idea who is determining effort and who is determining flow. And both effort and flow cannot be determined by the same subsystem, by the same end on the power bond. Okay. So I hope this concept, this idea about cause and effect is clear, input and output is clear to you. So if you have effort as an input to B, its output will be flow. And here the input to A is flow, the output from it is effort. Okay. Only then they can actually interact compatibly with each other and they can transact energy, they can transact power. Okay. So this information of transaction of power, it can be represented in a very nice manner, very elegant manner, using a simple stroke which is called as a causal stroke, and on the bond graph it is represented like this. So let's take the subsystem, the system that we just discussed. We have the subsystem A and the subsystem B, and there is transaction of power between them. And let's also say that A is determining the effort and B is determining the flow. So how do we represent this information graphically? We are not going to use these single arrows in our bond graph. So how do we model this? How do we represent it? This is the flow receiving end and this is the effort receiving end. What we do is we place a simple stroke. You see this? This stroke. This stroke is what we call as the causal stroke, and it is placed on the end which receives the effort. As simple as that. Automatically the other end receives flow. Okay. So it's a unique way of representing who is providing effort and who is providing flow. So that settles the idea of representation of cause and effect in terms of efforts and flows. So power is represented, transaction of power is represented, who is determining which component of power is also represented. In the same way, suppose instead of the previous case where effort was going from A to B, suppose we have A as the effort receiving end and we have B as the flow receiving end. Where should we put the causal stroke? It is to be placed towards A, because the end which receives the effort, it is the one on which the stroke should be placed. So this is a very simple yet elegant way of representing the cause and effect relationship in bond graph. Now let us look at a very simple mechanical system. In this system, we have a mass here